Actually, what I planned today for this advanced section was grid refinement, load balancing, and restarted and checkpointing. These three things. I'm not sure if we everything can do today, but we start simple with some. I prepared, of course, some slides, but I will skip it maybe, and we start directly with hands-on on our direct in the code. Okay, so again we can open open our laminar plane flow. So, and first of all, we can, of course, simple way add some refinement, anything. Yeah, this we can change in config file refine level to 1. So, and start again our simulation and look in the power view what happens. So, and should be the add refinement and the walls, yeah, and we will see this in the block grid, for example, and in the microscopic quantities file. If you switch in power view here to here, for example, 2 points, yeah, then we can see points, and we should see also this refinement. Okay, so I can simulate also. So
I mean, obviously there is somewhere in the code that it says the refinements.
yes, yes. I will explain. Yes. So actually, so we have for grid refinement we have this set of classes. Yeah, we have interpolator, we have this visitor for set connectors, interpolation connectors. Yeah, I said you we have special connectors, few special connectors for refinement. So, and we have this is special connectors. There is coarse to fine vector connector in fine to coarse vector connector, and we have for interpolator is abstract class, and we have implementation for compressible, compressible kernels and incompressible kernels. So, and if you return to the code, okay, I can stop it and again reload this in the so, and you can see, so you should have the same thing. So here refinement, yeah, on the walls, yeah, this is level 2 refined level as a one as we have. So for courses is level 0, and then we have level 1 and so on. Yeah, that's in our nomenclatures. We have here level 1. Yeah, this refinement. So, and in the code, if we jump to the line. Yeah, line 194. Yeah, you see this if statement is if refinement level greater 0, then we, program should does this stuff, okay? And here simple again, yeah, we don't need apply this on no, this only, okay, it's only this only for the output. Yeah, this with start refinement, because of course we apply this on all processes. Yeah, and again we have this helper again. Yeah, it means this helper we have some steps to organize this refinement, but it simplified for standard case. Yeah, if you don't need some fancy refinement or something like this, for standard case we use always this refinement course inside GB object helper. It means we set some geometry object, it's add object, yeah, in this case, and second parameter is refinement level, in our case is 1, and then this helper take care about rest, okay?
Okay, so actually, wait, refinement level, no, you specify the refinement level there in, so the line that we don't see now.
I highlighted here, you can see parameter, first parameter.
Yeah, but on, no, the line before that.
Line before that.
Yeah, so there's refinement level.
Okay, yeah. Also here is hard coded, and
so what does this then do?
this is yeah, you define always maximum refinement level, okay? It means which your maximum, because you can have more refinement levels, okay? And typical also,
okay, so this will recursively refine if you put it to 3.
Yes,
okay.
Yes.
And then what does the 1 specify here in the refinement helper?
That this object is it should be refinement in this object to refinement level 1.
So it will maximum refine, we will maximum have 1 level refine.
Yes.
Or else we would have refined it instead of 1.
Okay, so you could add, you could add another object with further.
Yes, we can add another object with for example, for next refinement level. Yeah.
Okay.
For example, what should you notice? It's of course the refinement happens first on the block grid. Yeah. So if you look on the block grid here, because the topological, yeah, that's each block then split it in 4 blocks, you can say. So, and we need also some place for interface, yeah. So in this case, okay, I maybe show you again this picture. So yeah, you see, this is block which start here. We start refinement, yeah, and the block is divided in this case. Okay, we have 2D, yeah, in 3D we have 8 blocks, and 2D we have 4 blocks, and you see this green part is interface blocks, yeah, this interface blocks for refinement. So, and here interface blocks for this green interface blocks for coarse level, and this blue blocks are for fine level. So yeah, and you can see it's always yeah, we need some space for this interface. At least you need a block, a coarse block, yeah, to produce interface. Okay, at least one coarse block. So then you should create your geometry for refinement, yeah, with thinking about this, yeah. Okay. Yes.
But we didn't, I don't know, like we didn't change anything in the config file for regarding the blocks, but then the blocks increased when we did refinement. So does it by itself?
No, because we defined only this bounding box and fill this with coarse blocks, yeah. And then we apply refinement, and the program splitted this coarses block and fine blocks, yeah. And of course you have then more blocks after that operation, yeah. But yeah, you don't have much control on this, yeah. It's automatically.
You only have one parameter to control in the configuration file, which is the refinement level.
Yes. How many refinement levels you have? So, and you control, of course, with this geometry object. If we look in the paraview, we can open in Geo. We have this refinement cube. So 1 and 2, okay. So if we open this, so this is, yeah, we define here refinement area with this geometry, and you can see it's covered with one coarse block, yeah. And inside this geometry there's this helper called inside and across, yeah. And this block cross this geometry, and this grid generator generates this fine blocks inside the coarse block, and then create yeah, this interface, interpolation cells, yeah, this and special connectors for this. It's everything automatically done as a yeah, it does this helper first, then second part is again, you see the section, if refined level greater than 0, we need to call this visitor is simple set so-called undefined nodes. Why we have undefined nodes? Because you can see if this interface, yeah, as a grid interface between two grid levels, then it stays a line of nodes here that will be not used, and yeah, not here, here, yes, in course 1, yeah, this in course 1, and because okay, we have solid nodes, fluid nodes, we don't allow apply some collision operator on these nodes, and we set these nodes in undefined, okay, and then kernel ignored these nodes, simple. These nodes here, yeah, these nodes will be ignored because we don't need this. So this second part, which we but important thing, why stay here, not direct in this helper, yeah, because we generate only block grid without nodes, yeah. and after we apply this set block visitor, set kernel block visitor add nodes to the blocks actually, yeah. And then after that we have nodes in our grid, and then we can apply this undefined nodes visitor. The same is also for helper, this interactor helper, yeah. We call this set BC only after we have nodes in our grid. Because after call, as its order very important, yeah, because if you apply early, you don't have nodes, and that's nothing happens. So you have an empty grid actually. So okay, actually that's it, and we can you have always some object here in the middle, yeah, this airfoil, and we can try to add refinement to this object, okay. And we can try simple the same stuff, actually create cuboid object, surround this around our airfoil, and add this object here in in refinement helper, okay. So please, okay. So okay, then I simple go ahead next parts. So okay, second thing what I plan to talk about is load balancing, yeah, because if we have as important always if we have some parallelization, how we divide the load between processes, and for this domain decomposition and load balancing, we use a third-party library called Metis. So, and in the code is there is implemented or this interface to this to the Metis libraries implement Metis partition grid visitor, and this this grid visitor has two important parameters. This recursive cave, I can show you in the code. So here, yeah, this line 139, we define this Metis visitor, and you see, so this parameter, the second parameter, first parameter is communicator, second parameter is level base, no, just a moment. Okay, sorry, it's other aspect, but okay, if we go to the definition of this, yeah. So we have this parameter graph type. So, and then part type. So part type means this again recursive or cave. It is parameters of this Metis library. Yeah, Metis is a graph-based partitioner. They use graph theory to to divide your simulation domain in some parts with the same load, yeah. And with these two parameters you can control which algorithm use the Metis, yeah. And exist two options. One is recursive. It means it works pretty good for simple geometry. If we have, for example, like here, simple channel flow, yeah, there's some box, and you need and nothing in principle, nothing to inside, for example, this box, yeah, this channel flow, nothing more, yeah, and recursive is in produce good load balancing. Yeah, it's simple. Try recursive to divide so domain, yeah, in um, the equivalent parts, so we can say, yeah. And other parameter is cover more complex algorithm, but it also better produce better result for complex geometry. Yeah, like here, if we have some airfoil, yeah, not so trivial shape inside your channel, then better way is use this K-way parameter. Okay. On second set of important parameter which influence your load balancing, yeah, is this level intersected and level based. So, and yeah, this graph type as a second parameter. So if we look again, so we have this level base. What it means? It makes it play role only if you have refinement, okay? Because if we have refinement, then blocks on different level have different amount of work. We know from theory we need to apply the collision operator 2 times on the fine level before we apply 1 time on the coarse level. Yeah, we have always this more work on the fine level. And okay, the logical how we can then divide our load, yeah, if we have refinement. The one way is we look on the we define some load weight for each level. Yeah, we say, okay, on the level 0 is weight 1, for example. Each block has for load, and on the level 1 is 2 times, for example, more. Yeah, this weight 2. And then we try to apply METIS for entire grid, and METIS METIS notice these weights, yeah, and put blocks with different weights, but that in the sum each process has the same amount of work. Okay, it could be different coarse blocks and fine blocks, but if we do this, and this is this parameter level intersected, yeah, it means this, yeah. But if we do this, it causes other problem, that we have our order to applying this collision operator, yeah, for different levels. So as I say, and then we have some, so simplify, the coarse block should be then weight on fine blocks, yeah, because this dependence. We cannot apply this interpolation before the fine blocks are ready with collision. So, and this is issue, yeah, and the default value for this parameter is level based. What does mean? We apply METIS for each level in the in the grid separately, and then we have the same, or approximately the same load again for each process, but then it's separately for each level. Okay.
So I think there's also the other issue with memory. What don't you think?
Yeah, maybe, but main argument for this level based is because we have then delay, in the this main loop actually. Okay, but trust me. So use this. You can try. Yeah, this is homework. Yeah. It was the plan. You try one parameter, other parameter, and compare your performance, for simulation, and and you will see which parameter is better. Okay, which load balancing then is better, and the same for recursive and this K-way. You can also apply different parameters and look for the performance. Yeah, sometimes it's not clear exactly. Sometimes if you have some geometry, some not clear which this recursive or K-way you need to use, because it's some third-party library, in principle the black box, and you need to try this parameter to achieve optimal performance or optimal load balancing. So then homework you can try. You don't need a lot of implementation. You just look in this part and try to play with these parameters and look on the performance, how it influence on your performance. Okay.
Of course, only this doesn't do anything on your laptop.
This other, but of course you need to start your application parallel, because it makes, you see, this MPI it works, or this Metis partitioning influence performance or makes sense only if you have distributed memory. If you use MPI. So if you use threads, like we do it every time today, we use only threads, then of course doesn't matter, because then you have for threads. Okay, for threads, you can also tune this OpenMP. This is also another homework. You can try tune OpenMP first for threads, and this can you do in simulation. In simulation class here, simulation CPP, and at the head of this, file, you see you have this OpenMP scheduler definition, defines this macro definition, and here we have guided. As on most cases it works pretty well. But you can tune it, with other parameters. You can Google. It's different for this OMP scheduler. This standard OpenMP so definition, variable. So which this is dynamic, I think, and other. But typical is it depends of your hardware. So you can tune OpenMP with this in this line, but I would say it's bring not so much as a tuning if you have MPI and you tune your this Metis, for example, partitioner. So, but it's opportunity is here. So, and but if you want to play with parameters for Metis, you need to know how you start with MPI. Yeah. So for this purpose, we have MPI exec launcher command. Yeah. You type simple here MPI exec, then we need parameter minus NP, this number of processes. Yeah, and we say, okay, I have 4 cores and I can start 4 processes. Of course, you should set your number of threads of 1. Yeah, then we have only 1 thread per process for better utilization and clear result of performance management, for example. So, and then so the same thing, your binary, yeah, and with binary with config file. And if you start this, it doesn't work in container. Yeah, if you don't use container, it should be work out of the box. If you have installed if you have been installed this MPI framework, but in containers installed, but doesn't work, why is described here. Yeah, per default you work in the container as a root user, and the MPI says you, okay, this dangerous to start something with root, then yeah. But you can ignore this, okay, yeah, because it is in container. Okay, if you broke something, you write some malicious software, you destroy a container, but your system should be stay. So
why would I destroy anything by?
Yeah, they stay also here. Yeah, because you can overwrite something, some critical folders, for example, some system folders. Yeah, because the general issue. Yeah, because root as a god of the system, it has all right to write in all part of your file system and so on, and you can overwrite some file and with critical for operating system or something like this, on delete something, yeah, and then your operating system doesn't work more. But it's not so pretty critical for the container, because okay, you can build again your container, restart your container, you have always this clear operating system, yeah, and we know, okay, this this program should be okay. Then we should apply add this option. Add this option in our MPI exec command. Yeah, in case of container. Yeah, and you see the simulation started parallel in the MPI. Yeah, you see in the parts where we not use this if for output. Yeah, if ID my ID 0 equals 0, each process write the same the same stuff. You see, it's not consistent. Yeah, this should be for each output this check if it's 0 or not. This so okay, I'll stop it this first.
If you are on a cluster and each node has, say, 16 cores, then what you would do is you would run with 16 threads on as many nodes. that you could have, right?
Yeah, it depends. Yes, this is an option. Yeah, it depends how you want to utilize your hardware. Yeah, you have an option. Start on each node more threads. Yeah, on, for each node one MPI process with amount of threads equal to this local CPU cores, or you can start everything in MPI. Then it means for each core you start one MPI process. Yeah, logical. It should be this MPI, this combination OpenMP MPI variant should be faster, but it's also not always the case. Yeah, you need to try. It depends on your test case, on how is configured cluster and so on. Yeah, it depends of different aspects. It's better way, of course, try both. Do some small performance tests with these different options and look which is the performance and choose then better configuration for a simulation. Yeah. So, of course, advantage of this combined execution of the simulation as a combined MPI with OpenMP is that thing that because each process, if you have some output file, or in typical we have then a parallel output file for VTK. So then each MPI process write one this VTK file, okay, and of course it's also for post-processing. Yeah, working in with the ParaView. Yeah, if you have 12,000 cores, yeah, it's then the question what then you have 12,000 files. Yeah, and again the question how efficient ParaView open or how work this parallel file system, which typical is on the cluster. Yeah, each beta works with more small files or less big files. You know, it's also important aspect. How works this I/O? Yeah, the admins of the cluster typical says, okay, the system better works with less number of files, but my experience says it's not always the case. Yeah, it's you need again to try to experiment a little bit with, because it's always the different this implementation for parallel systems, file parallel systems. Yeah, but it's yeah, this is the price for working on the cluster actually. Yeah, because yeah, you have always different hardware and different software on this cluster, and this always a work. So okay, then I jump to next thing. Okay, the last what I want to taught you today, this restart checkpoint. Why we need this? Yeah, I taught you early on the cluster is special for the cluster in principle. But okay, if you have all the long run with your simulation on your local computer, for example, yeah, in typical you need more hours, for example, or days, yeah, and again it can be something happens, yeah, for example, housemaster turn off electricity in the building, yeah, and your simulation then is, yeah, and you need, okay, and disappear, your simulation disappear, and you need to, you have some primary result on in the middle of simulation, but it's not down, and you need to start for the at the start. You can start again, so from time step 0. And nice to have, of course, have some saving, this checkpointing, so call it. On the clusters, always you need this because you have limited wall time. You cannot run your simulation typical so long as down. You have limited wall time, and you can only run simulation, for example, 12 hours. If your simulation not down, it's your problem. So, and this, and for this purpose was implemented these 3 observers, simulation observers classes. So again, this is a part in the code. This is a part. Just a moment. So here. Restart. So, okay, I didn't explain important parameter for simulation observer. This is so-called this scheduler, UB scheduler object. Okay. With UB scheduler, we define one should be this simulation observer active, because the simulation class always notify for each time step observers, but we don't need always do something for each time step, very often we need do something only for some predefined time step or in some range of time steps, okay? And with scheduler object we can define, okay, if we go to this scheduler, we can see parameters, it's always, first parameter is step, so how big is step for this scheduler, it means on which step should be happen something, which step is important, and then begin from which step we begin do something or observe this observer should be observed, so called, and it's default. You see, it has default value. We start with 0 time step, and end. The third parameter is end. We end infinity as like what? Yes.
Is there a reason why this is a double?
Reason why this is a double?
So is it actually in the scaled time?
Actually it's always like integer, but this scheduler part of this basic part, this some general implementation, and it was part of this legacy code. It was so implemented, and we don't change this.
Okay.
Maybe it was some reason for this, but actually, in the actual version, it will be used some integer numbers, like it's simple casted to the double in turn this scheduler. But if we look here, okay, it's defined for real because we need a real number for this. But if we look in the config file for this to this step starts step, which step we want to write this checkpoint, yeah, and from which step we started. And in this case, I have only one checkpoint. Yeah, I want to have one checkpoint in my simulation, and it is in this case at the end of the simulation. Yeah, because end time is also 1 million. Okay, and if simulation is down, then write this checkpoint. But typical or usual, you define here, for example, 1000, then or other time step, and start, for example, also from 1000, then program write each 1000 time step one checkpoint. Okay, so also you can also try to play with these parameters and look what happens. So, and okay, I have a time, yeah, so a little bit as a very pretty briefly about difference between these three observers. What is difference actually? Okay, the first one, yeah, the simple MPI, and yeah, important things is this restart checkpointing mechanism use MPI IO file. Yeah, this special implementation in MPI library, it's produced some file which very optimized for this parallel file system. What typical is on the cluster, yeah, because cluster don't use this standard hard drive and so on. As typical, you have so-called diskless nodes on the cluster. Yeah, it's no disks, nothing. It's only processor RAM and very lightweight some version on operation system. And but how is processes with this all files? For this purpose, use it a special parallel file system, this distributed file system, very complex, and this typical MPI library which runs on the cluster is also some implementation which optimized for this cluster. And this implementation, because MPI is, it is not library, yeah, it's not only standard, but how this standard implemented is depend on provider, this software, or and usually you have some yeah, producent of this cluster, and this provide also software. And this MPI IO usually optimize for this parallel file system, or very efficient utilize this parallel file system. Yeah, because if you try to use standard interface of operation system to work with the files, yeah, it can be very slowed your simulation and entire cluster. Yeah, then it can be not only, it can be could be not bad, not only for you, also for other users. And this is the sense why admins always try to yeah, try to say users use this MPI IO. Okay, so okay, and okay, this first restart simulation was very simple. Yeah, we have many processes, many MPI processes, and we have this parallel file. Okay, and each process write his part in this parallel file. So then if we want to restart our simulation, then it works very fast, yeah, because it's straightforward. We have, for example, we have n processes, and each process write the data in his part of this MPI-IO file. The advantage is very fast. Disadvantage is if you restart your simulation, you have to have the same number of processes, yeah, but it is not always possible, or because, yeah, it's, of course it's possible, you can do this, but usual. So for example, okay, you decide first start your simulation with, I don't know, 10 nodes, yeah, but because, okay, you have you see in the queue is available 10 nodes, and I know it's enough memory, and for my simulation, for maybe for 4 nodes, but I have 10 nodes, and it should be faster, yeah, 10 nodes and better as the 4 nodes. But minimal requirement, for example, if you know how many memory on the each node, and how memory can consume your application, and you see, okay, you can run your application at least 4 nodes, for example, yeah, but you see in this information available nodes in queue on the cluster, and you can see, okay, it's 10 nodes, yeah, okay, I start with 10 nodes, yeah, because it's of course faster, yeah, you parallelize your data, it's faster, and next time after this wall time, your simulation is done, and you want to restart this, and you see, okay, now I have 9, for example, now 9 free nodes, and I cannot restart my simulation, but actually it's enough, yeah, and from memory point of view, it's enough. Okay, it's a little bit slower then, but I can live with this, yeah. It's okay, because better I start now my simulation as I wait maybe 4 days, because before I have this 10 nodes again, you know. This is always the game. So, and then, okay, this then is it not good option, yeah, in this case. And yeah, but the restart is very fast. Okay, faster because it's straightforward read the data direct from this file, but we don't have this flexibility to change number of processes. So, and for this flexibility, we implemented this migration simulation observer, yeah. And here we don't write in this parallel file, MPI-IO file, not each process write his part, but we write each block in order, in predefined order. Yeah, this from 1 or from 0 block, or from 1 block in this case until up to n. Okay, and we can say this in sorted order. Okay, we write the blocks, and we can then what is the sense here? If we restart application, then each process can be easily find in this parallel file the blocks which are part of this process. Okay, So the problem here is as slow as the first variant, yeah, because we need to search the blocks, okay, and of course we this it has more more read and write operation, yeah, because we each operated only with blocks, yeah. In first variant we directly write this amount of data which part of this process, yeah, and here we in small portion we write or read in small portion, okay. Disadvantage we need sometimes it's depend of system of your depend of size of your system, yeah, it can be take time, yeah, this write and read process, and you should calculate this in your yeah, how you apply this restart checkpointing, for example, yeah, in your sim. I mean you need to see, yeah, wall time and so how many time steps you want to achieve in your simulation run, and yeah, you need to, yeah, to yeah, to think about this, okay. And the problem was here, yeah, why is this so slow? Because it's you have a lot of I/O operations, yeah, at least. And then we think about, okay, maybe we can optimize this and instead have a lot of MPI I/O operations, yeah, for reading, writing this. We can do something in between, so something combine it. First yeah, approach and second approach. And it was implemented this migration BE simulation observer. BE means blocks exchange, yeah. This again, this is combination of these two approach, this array of processes, yeah, with data migration. What it means, it you write and read data, yeah, for each process in this MPI file, and if you restart, yeah, so the checkpoint, the write checkpoint is the same as in first approach. By reading, you read then this part, and then apply this method decomposition again for your simulation, and look which block is part which processes, and exchange this in network. So yeah, then it means you have the same speed for writing, but more time. You need more time for reading, yeah, because this exchange, but maybe less time as a second approach where you read each block, you know. But it always again is depend how is implemented or which infrastructure for network you have, or how which MPI I/O. What I observed, sometimes you have the second variant is faster as the third variant. Sometimes third variant is faster. Yeah, again you need to try. Before you start your production run, you make some small tests, yeah, better prioritization, better checkpointing, so, and then you can decide, okay, this is optimal variant, and start your production run. So, okay, that's it for this advanced section, and I think I'm good in time. So, any question, or I stop the recording now?